So what on earth could an ancient Greek sea battle possibly have to do with that supercomputer you carry around in your pocket? Well, as it turns out, pretty much everything. We're about to go on a journey that connects a 2,000-year-old philosophical puzzle to the very technology that keeps our digital world from, well, completely falling apart. This is the incredible story of how we learn to reason about the future.
Let's start with a question we've all probably asked ourselves at some point. Is the future a single straight road that's already paved? Or is it more like a garden of forking paths where every single moment branches out into a whole new universe of possibilities? For literally centuries, this was a question for philosophers. But then, something wild happened. It became one of the most urgent problems for computer engineers to solve.
The ancient Greeks had a name for this problem: future contingents. Okay, think about this statement. There will be a sea battle tomorrow. If you say that's true right now, doesn't that kind of imply the future is already set in stone? But if you say it's false, well, the future still feels decided just in the other direction. It's this brilliant logical trap that seems to completely erase free will. And for thinkers like Aristotle, that was a really, really unsettling thought.
For hundreds and hundreds of years, the sea battle paradox was just stuck. It was a philosophical debate with no end in sight. But then, in the 20th century, a new kind of thinker entered the ring, the logician. And they had a crazy, ambitious goal: to stop just arguing about time and instead to build a formal mathematical language to actually reason about it.
Now, this journey from paradox to proof took a long time. Things really got moving in the 1960s with a logician named Arthur Prior, who forged the first real tools for this stuff. But then, the really amazing part happened. In the 70s and 80s, computer scientists, guys like Amir Pnueli, Edmund Clark, and Alan Emerson, stumbled upon Prior's very abstract work. And they had this incredible aha moment, realizing this philosophical toolkit was the exact thing they needed to solve a brand new, very practical problem.
Arthur Prior's big insight was this: talking about the future is fundamentally different from talking about the present. Saying the sky is blue is a fact, but saying there will be a sea battle, well, that's a statement about possibility. He realized that when we talk about the future, what we're really doing is navigating a whole space of potential realities. And that one simple idea, it changed everything.
So Prior took this insight and turned it into a real system called tense logic. He came up with these simple operators, like P for talking about the past, and F for what could happen in the future. For the very first time, we had a kind of grammar for time itself. We could finally build precise, logical sentences about what has been and what might be.
And you know what? This super abstract philosophical toolkit showed up at the perfect time. Because just as logicians were figuring out how to talk about time, computer engineers were starting to lose control of it.
By the 70s, computers weren't just simple calculators anymore. They were complex beasts, juggling dozens, even hundreds of tasks all at once. Think operating systems, air traffic control. The question wasn't philosophical anymore, it was terrifyingly real. How can you prove, 100% prove, that two planes will never, ever be assigned to the same runway? Just testing it isn't good enough. You need mathematical certainty.
And this is where Amir Pnueli had a moment of pure genius. He took Prior's logic and adapted it to talk about computer programs, creating something called linear temporal logic, or LTL. LTL basically looks at a program's execution as a single, straight timeline. It lets you prove things like, this request will eventually get a response. But in doing so, it made a huge philosophical bet. It assumed there's only one future path you need to worry about.
And boom. Just like that, that ancient Greek debate about determinism came roaring back. But this time, it was happening in the world of silicon and code. Is the computer system's future a single predetermined line, or is it a massive branching tree of possibilities? Okay, so this set up two totally different ways of looking at the world. On one side, you have LTL, the linear view. It sees time as a straight line. It can only ask questions about the future path. But on the other side, a new idea emerged, branching time logic, or CTL. It saw a computer's future as this huge tree of possibilities. And this let you ask much, much deeper questions, like, is it even possible for the system to crash? Or is a good outcome inevitable from this point? See the difference? It's huge.
The linear view. It makes sense, right? When you run a program, you only see one thing happen. Pnueli's logic was all about analyzing that one specific path, that single sequence of events you actually observe. But
Then Clark and Emerson came along and said, whoa, hold on a second. Looking at just one path is dangerously naive. Real-world systems have to deal with all sorts of unpredictable stuff, user inputs, network delays. To truly prove a system is safe, you have to consider every single possible path it could ever take. Its future isn't a line, it's a vast, sprawling tree of computations. The Garden of Forking Paths was no longer just a cool idea from a story, it was literally the blueprint for how software actually works.
And this big shift in thinking, from a single line to a branching tree, this wasn't just some academic squabble. Nope, it was the absolute key that unlocked a revolutionary new technology for making sure our digital world is safe and reliable.
That technology is called model checking. The best way to think of it is like a super-powered, unstoppable detective for your code. You give it a model of your system, that whole tree of all possible futures, and you give it a rule, something simple like the elevator doors must never open while it's moving. Then, the model checker goes to work, exhaustively exploring every single branch of that tree, looking for any possible future, no matter how unlikely, where your rule gets broken.
And the whole process is just so powerful. First, you model your system. You map out its entire universe of possibilities. Second, you write down your rules using that branching time logic we talked about. You're basically defining what good behavior looks like. And finally, you hit go, and the algorithm checks every single possibility. It comes back with something no amount of human testing could ever give you, a definitive proof.
So, just how big can these trees of possibilities get? I mean, they must get huge, right? Oh yeah. In the early days, that was a massive problem. But then a breakthrough called symbolic model checking let these tools handle systems with a truly mind-boggling number of states. We are talking 10 to the power of 20 and way, way beyond. That is more possible states than there are grains of sand on every beach on Earth. And this technology checks them all.
So where is all this heady philosophical stuff actually being used today? Oh, just everywhere. This branching time view of the world is used to prove the microprocessor in your laptop won't fail. It's used to guarantee an autonomous car's safety logic is solid. It's used to make sure the cloud services we all depend on don't just fall over. Seriously, every time you trust a complex piece of technology, you're basically trusting the ghost of that 2,000-year-old idea.
And that right there is the punchline to this whole story. That ancient abstract struggle to figure out if the future is open or fixed, to figure out if there was going to be a sea battle tomorrow, it ended up giving us the exact intellectual tools we needed to build, and more importantly, to trust our modern digital world.
Which, of course, leaves us with one last thing to chew on. As we build things that are even more complex, AI, quantum computers, that tree of possible futures is only going to get bigger and weirder. So the question is, what new kinds of logic, what new ways of thinking about possibility are we going to have to invent to make sure we can still trust them?